This is the King Tiger. It was arguably one of the most powerful German tanks of World War II. As the successor to the Tiger I, it was designed to serve as a spearhead tank for offensive operations. While it was an awe-inspiring design, it was not as successful on the battlefield as its designers and the German leaders had hoped. We've modeled the King Tiger in intricate detail to showcase both the features that made it legendary and the flaws that led to its downfall. In this video, we focused on the most widely produced model, the Henschel turret version. My name is David Webb, and this is Blue Paw Print. The King Tiger was a massive vehicle, significantly larger than its Allied heavy tank counterparts, such as the M26 Pershing and the IS-2. The King Tiger's hull was 25 feet long, increasing to 33 feet 9 inches, with the main gun barrel at full forward position. The tank was 12 feet 3 inches wide and 10 feet 2 inches tall. The King Tiger was also by far the heaviest standard-produced tank of World War II. Its combat-ready weight was 154,000 pounds. The crew of the King Tiger consisted of 5 men. The commander sat at the rear left of the turret, directly behind the gunner, who was positioned at the front left next to the main gun. The loader was opposite the gunner on the front right side of the turret. In the hull, the radio operator sat at the front right, while the driver was seated at the front left. The King Tiger's armament consisted of a primary weapon, the 88mm Kampfwagenkanone 43L71, and 2 7.92mm machine guns as secondary weapons. Though used on other vehicles, the 88mm gun was the King Tiger's signature weapon. Originally designed as an anti-aircraft gun, the 88mm gun proved its worth against Allied and Soviet tanks in the early stages of the war. As such, it became one of the main reasons for creating the Tiger tank series. Due to its smaller size, the Tiger I was equipped with the smaller, less powerful version of the gun. The King Tiger was large enough to carry the weapon in its original size, which had a significantly superior muzzle velocity. The gun had a barrel length of 20.5 feet and a caliber of 88mm. The 88mm gun had to undergo a series of modifications to be used as a tank weapon. A muzzle brake was added, redirecting gases to the side of the barrel to dampen the recoil. Air was also blasted through the barrel to clear fumes after firing. Another significant modification included a pair of shorter, fatter recoil cylinders mounted just above the gun barrel. The right cylinder, a hydraulic recoil control cylinder, was designed to provide maximum shock absorption when fired. The cylinder on the left was hydropneumatic and built in 2 sections, a gas and a liquid section. The gas section of the cylinder brought the long, heavy barrel back to its original position, while the liquid section ensured this movement was done smoothly and safely. If the tank had to be abandoned, the crew could drain these cylinders and fire the main gun. This would cause the gun to recoil forcefully into the back of the turret, rendering it inoperable. The King Tiger's 88mm gun was undoubtedly the most powerful tank gun of the war, capable of firing projectiles at high muzzle velocities, ranging from 1,968 feet per second to 3,707 feet per second, depending on the type of ammunition used. Trials showed that the King Tiger was capable of hitting a target with 100% accuracy at distances of 1,093 yards. At a range of 2.1 miles, the accuracy was reduced to 50%, which was still an impressive feat. In actual combat scenarios, these accuracy percentages were generally lower due to range estimation errors, environmental conditions, and battlefield stress. Oberstleutnant Alfred Rubel said, T-34 and T-43 tanks could be knocked out in favorable firing conditions at ranges of up to 3,000 meters. frequently as in the West, the Russian tanks avoided combating Tigers or turned away after the first tank was knocked out. The Tiger II has proven itself in every way and is a weapon the enemy fears. Some historians argue that the gun was too powerful for the targets it was designed to overcome. Its incredible size caused extended reload times and reduced ammunition capacity, both significant drawbacks when in the field. The King Tiger used two types of armor-piercing shells. Its primary round was the Panzergranate 3943. This round was specifically designed to handle the 88mm gun's high internal barrel pressures. The projectile featured an armor-piercing cap designed to penetrate sloped armor by reducing deflection upon impact. A ballistic cap placed over this armor-piercing cap enhanced the shell's aerodynamic performance, improving its speed and accuracy at longer distances. The shell also had a tracer and driving bands for added stability and accuracy. After loading the Panzergranate 3943, the gunner would electrically trigger the charge using a lever. An emergency button provided a failsafe in the event that the lever failed. When fired, the projectile traveled through a rifled barrel. The shell's two smooth driving bands were made of soft metal and tightly fit to the barrel walls, causing the barrel's rifling to spin the round. Though this increased the King Tiger's accuracy, it also caused increased wear on the barrel. Upon exiting the barrel, the Panzergranate 3943 accelerated to 3,340 feet per second. The tracer at the bottom of the projectile burned with a bright-colored light, allowing the crew to see the projectile's trajectory so they could adjust the aim for the next round. Upon hitting the enemy armor, the ballistic cap would split, making way for the armor-piercing cap underneath. This armor-piercing cap was made of a softer metal, flattening as it struck the armor, sticking to the enemy tank and preventing it from ricocheting while allowing the projectile to penetrate the enemy armor. This design allowed the Panzergranate 3943 to penetrate armor up to 8.6 inches thick at a distance of 550 yards. Immediately after penetrating the armor, a detonator in the bottom of the projectile would be triggered. A small charge of amatol would explode the projectile from the inside, providing maximum damage within the enemy tank. Against more heavily armored enemy vehicles, King Tiger crews used another type of shell, the Panzergranate 4043. The design of this high-velocity type of shell included a tungsten carbide core, allowing it to pierce up to 9.9 inches of armor at 550 yards. However, since tungsten was scarce, crews rarely used this shell. To aim, the gunner used the TZF-9D, a monocular telescopic sight mounted on the front section of the turret. The TZF-9D had a dual magnification system with levels of 2.5x and 5x, allowing gunners to switch between wider fields of view for target acquisition and higher magnification for precise aiming. A marked reticle assisted with range estimation and target lead. An outer dial was used for the range setting with 4 separate scales for each shell type. The tip of the reticle's center triangle marked the desired point of impact. The small triangles on the left and right were used for moving targets. However, they could also be used to measure range. The heights and widths of the triangles, as well as the spaces between them, were expressed in milliradians. A milliradian covered 1 meter at 1,000 meters, or 50 centimeters at 500 meters. With these triangles and with the gunner's knowledge of the size of the enemy vehicles, they could calculate the range. For example, if a T-34 tank in the side view filled 10 milliradians in the sight, that would mean it was at a distance of 0.41 miles. The King Tiger was equipped with 2 7.92mm MG-34 machine guns. The first was a coaxial machine gun mounted alongside the main gun in the turret. It was operated by the gunner using a special pedal and shared the same sight as the main gun. The machine gun was fitted with a brass catcher to prevent casings from dropping on the floor by directing the spent ammunition into a bin. The radio operator used a second MG-34 mounted on a ball mount on the front right part of the hull. In addition to using his hands, the radio operator could aim the gun using a special metal half dome attached to the machine gun. By placing his head into the dome, he could guide the machine gun through his head and body movement. The King Tiger was also equipped with a grenade launcher, the Nahverteidigungswaffe, or close-range defense weapon. This spring-loaded launcher was mounted on the turret roof and could be operated from within the turret. It was designed for firing various types of ammunition, including smoke grenades for concealment, flares for signaling, and anti-personnel grenades to defend against infantry attacks. Since it was planned to act as a spearhead in breaking heavily defended enemy territories, the King Tiger was designed as a heavily armored vehicle. Its hull was built from hardened steel plates. The upper glacis plate was 5.9 inches thick and angled at 50 degrees, giving a relative thickness of 8.3 inches. During our research, we found no instance of the front upper plate armor being penetrated in a combat situation. Let us know in the comments if you know differently. The lower glacis plate was somewhat thinner, measuring 3.9 inches. It was also angled at 50 degrees. The upper and lower plates were joined together using interlocking joints to minimize weakness where the two plates met. The upper plate was significantly thinner, constructed from 1.57-inch steel. The front section featured a bolt-on plate with a vent and hatches for the driver and radio operator. Each hatch used a lift and rotate design, allowing it to be opened even by a wounded crew member. In front of the plate were periscopes for both the driver and radio operator. The driver's periscope could also rotate to a limited degree, providing a 100-degree field of view horizontally and 25 degrees vertically. The radio operator's periscope visibility was much more limited. Positioned at an angle and fixed in place, it provided only a 60-degree horizontal and a 10-degree vertical field of view. The front section of the floor was built using 1.57-inch steel plates to protect the driver and radio operator from landmines. The rear section plate was just 1 inch thick. The rear plate was constructed from 3.15-inch hardened steel. The hull's side plates featured the same armor. The front was the thickest part of the turret's armor, built from 7.1-inch thick steel and angled at 10 degrees to provide a relative thickness of 7.2 inches. The elongated gun mantlet, known as the Saukopf or pig's head, was specifically designed to be resistant to attacks and prevent shells from jamming the movement of the gun. Its maximum armor thickness was 5.9 inches. The sides and the rear of the turret were equipped with 3.15-inch armor. To rotate its heavily armored turret, the King Tiger utilized a hydraulic system powered by a pump connected directly to the tank's main engine through a drive shaft under the turret basket. This meant that the engine's rotational speed dictated the turret's rotational speed. With the engine running at 3,000 RPM, the turret could complete a full 360-degree rotation in less than 10 seconds. However, the rotation system was prone to malfunctions at such high speed. The standard full rotation time was 19 seconds, which would be achieved at an engine speed of 2,000 RPM. The turret's electrical systems were powered by the tank's main batteries, which were placed next to 2 of the 7 fuel tanks. The turret ring had a diameter of 72.8 inches. Its large size was necessary to provide a stable base for the turret and the gun. The entire design of the tank turret was largely influenced by the unique gun that it housed. The elongated shape of the King Tiger's turret was necessary to balance its unusually long cannon. The gun was mounted asymmetrically. This adjustment provided more space for the gunner without further increasing the already large turret size. The gunner was positioned to the left and controlled turret rotation using floor pedals and a backup lever located under his left arm. As he brought the aim closer to the target, he switched to a manual traverse system positioned between his legs for more precise aiming. For the gun's elevation, the gunner used a hand wheel located to his right. The elevation mechanism was assisted by compressed air from a compressor under the gunner's seat. When the system was active, the almost 2.5-ton gun could be raised and lowered with ease. Once the target was in sight, the gunner would release a lever on the turret rotation handle to lock the movement of the gun and hold the aim. An azimuth indicator was placed in front of him to prevent the gun from losing track of the turret's position relative to the tank hull. The azimuth was positioned so that it could also be seen by the tank commander seated right behind and above the gunner. The turret cupola had 7 periscopes arranged in a circle for a full 360-degree view. The commander's hatch could be opened by first turning a screw, then pushing a lever to fully open it. Once open, the hatch could be locked to prevent it from swinging shut while the tank was in motion. Opposite the gunner and commander was the loader's station. Although the loader had a retractable seat, he would usually stand during combat to load the gun. He had his own hatch and a periscope. The loader's station was equipped with an additional manual turret rotation handwheel, allowing the loader to assist the gunner with turret rotation when needed. Ammunition was stored in racks at the back of the turret and along the walls of the hull. This ready rack could hold up to 22 shells for fast reloading. 48 additional shells were stored along the hull walls for long-term storage. A standard loading procedure required the loader to take a round from the ready rack, lay it down on the roller, and load it into the gun chamber. After the gun breech was closed, the gun was ready to fire. A well-trained soldier could perform the entire operation in just 8 seconds. Some crews preferred to keep the ready rack empty out of fear of ammunition cook-offs, which could occur if the turret sides were penetrated. Keeping it empty also allowed access to the hatch at the rear of the turret. In an emergency, getting out of the top hatches would expose them to gunfire from all directions, whereas evacuating from the rear hatch gave some cover. To create an extra layer of protection for the ammunition inside the rack, links for spare tracks were placed on the outside of the turret. Tiger was powered by a 6-gallon V12 Maybach HL230 P30 petrol engine, sealed in a watertight compartment. This engine was very similar to the one installed in the Tiger I. However, cast iron was used for production instead of aluminum. This increased the engine's overall weight, but also increased its displacement by 1.6 litres, and thus its power. The Maybach HL230 could produce 700 horsepower at 3,000 RPM and 1,364.5 pound-feet of torque at 2,100 RPM. To prolong its lifespan, it was recommended to keep the RPM under 2,500. Theoretically, the tank could reach a top speed of 25.7 miles an hour on a clear road. In reality, its actual operational speed was limited to around 23.6 miles an hour. The engine featured a distinctive crankshaft design. Unlike standard crankshafts fitted with plain bearings and wings connected to the engine pistons, the Maybach HL230 had a tunneled crankshaft with rotary bearings. This design improved rigidity and allowed the pistons to sit closer together, creating a more compact and durable engine. The engine's 4 carburetors were fitted with air filters and drew air from a pair of armoured air intakes at the top of the engine deck on the access hatch. Further back was a third air intake. The King Tiger's Maybach HL230 was a gasoline engine, and the fuel for its operation was drawn from 7 interconnected tanks located within the hull. The tank connected to the filler cap was in the central rear section. Additionally, there were 2 tanks located in the sponsons, 2 at the bottom of the rear hull, and another 2 beneath the turret basket. Together, these tanks housed 227 gallons of gasoline. With an average consumption of just over 2 gallons per mile, it gave the King Tiger a range of 105.6 miles on roads and just 74.5 miles across rough terrain. 7 fuel tanks meant a maze of fuel lines connected the pumps that fueled the engine. That was another significant drawback of the King Tiger. With many couplings in hard-to-reach places, leaks were very difficult to detect, making fires a potentially serious hazard. To try and address this issue, the King Tiger was equipped with an innovative automatic fire extinguishing system. If the sensors detected temperatures above 120 degrees Celsius, the extinguisher would activate for 7 seconds. If the temperature remained high, the system would repeat the process. The engine was cooled by 4 radiators and 2 fans, separated into compartments on either side of the engine. The compartments were connected to the engine via a liquid coolant circulation system. A large crankshaft-driven fan was mounted between each pair of radiators and dissipated the heat. Since the fans were driven by the engine's rotational speed, when the engine's RPMs increased and the heat increased, the fans would compensate for that automatically. The King Tiger's engine could be started in several ways. The first was with the help of an electric starter. This option could only be used when the engine was warm. The second was the inertial method using a crankshaft, which could be operated 3 ways: by hand, with a rotary shaft from the engines of the Volkswagen Kugelwagen or Schwimmwagen, and using a gasoline-powered external starter. The driver controlled the tank with a special steering wheel, brake, accelerator, and clutch pedals. The steering wheel, an uncommon feature in tanks of the day, was connected to a steering box that adjusted the gear ratio for each track. When the wheel was turned, the track speeds would alter, enabling the tank to turn. The steering wheel was supplemented by a more traditional control lever for each track, providing a backup to the steering wheel. Pulling a single lever applied the brake to the corresponding track, causing the tank to turn in that direction. Pulling both levers brought the tank to a stop. Driving controls also included an instrument panel, a handbrake on the left side, a gear shift on the right, and a lever for switching between forward and reverse gears. The driver's seat could be elevated for driving with an open hatch, although in combat conditions, the driver would use a periscope. The King Tiger's drivetrain was arguably its weakest point. The components making up the King Tiger's drivetrain were credited with the most mechanical failures of any set of components. This was for one reason only: they were not designed for a tank of this weight. The King Tiger was intended to be fitted with a brand new drivetrain design that could be used both on the King Tiger and the Panther II. But when the Panther II project was scrapped, so was the development of most of the components it was designed to share with the King Tiger, leaving the King Tiger to be fitted with a drivetrain from the Tiger I, a tank 22,000 pounds lighter, and one that had already suffered reliability problems. The transmission used on the King Tiger was the Maybach Olvar OG40 12 16B, with 8 forward gears and 4 reverse ones. Since the transmission was housed at the front of the tank and the engine at the rear, the two were connected with a multi-joint drive shaft running under the turret basket. The transmission system suffered from significant overheating and had to be encased in an additional thermal cover to protect the driver and the radio operator. The final drive system delivered power from the King Tiger's engine to the drive sprockets that drove the tracks. The sprocket teeth connecting the wheels to the tracks often bent under torque, and the interweaved road wheels made replacing the inner ones challenging. The final drive system was the most overstressed component of the drivetrain, and its failure rate was incredibly high. By the end of the war, the average lifespan of the system was just 186 miles. This meant the King Tiger could travel approximately 2 full fuel tanks before experiencing a final drive failure. The transverse torsion bar suspension system consisted of 9 load-carrying axles per side, each connected to a wheel supporting the tracks. This design allowed each wheel to move up and down independently. It also increased stiffness during turns, enhanced stability over rough terrain, and enabled higher speeds. The wheels were arranged in 2 rows on each side, so that every wheel partially overlapped the adjacent ones, increasing the contact area between the wheels and the tracks. This configuration helped distribute the tank's substantial weight evenly, reducing ground pressure and enhancing mobility over challenging terrains. For dampening, the King Tiger had a shock absorber on each corner, connected to the frontmost and rearmost set of road wheels. The idler wheel at the very back of each track was mounted on a pivot. Using a simple wrench, it could be moved to the rear to tighten the tracks and forward to loosen them. Crew interaction was crucial in combat. Each member was responsible for a different task, and their survival on the battlefield depended on how well they performed as a team.
Verdammt, ich kann ihn nicht sehen. Nehmt Stellung an der Straße.
The driver was responsible for delivering the tank to an advantageous position with a good overview of the area. Choosing a good position was crucial as it allowed the commander to locate nearby targets through the cupola periscopes. Upon locating the target, the commander gave the gunner coordinates and ordered the loader to load a specific shell type.
Ziel auf 11 Uhr, Entfernung 800 Meter, Panzergranate 39.
The gunner then rotated the turret towards the target's direction. Using the system of triangles in his sight, he determined the exact distance to the target and placed it on the tip of the triangle within the sight. The gunner and the loader had to loudly confirm that the target was acquired
Ziel erfasst.
and the shell loaded into the gun. With the gun locked on target, the gunner and the commander would check the light signals to see if the gun was ready to fire.
Feuer.
The shell would leave the gun at a speed of 1,090 yards per second. The precision and power of the King Tiger's gun was exceptional. Near L'Église in Belgium, King Tiger 204 spotted a Sherman at 1.27 miles range. The crew fired, and the shell struck the target's frontal armor on the first shot, sending the enemy tank into flame. The King Tiger was an extremely effective vehicle that dominated the battlefields of both the Eastern and Western fronts. However, even though armor and firepower helped win battles, logistics won the war, and the King Tiger was a terrible burden for German logistics. As one veteran of the 503rd Heavy Tank Battalion said,
1 hour of Tiger operation requires 10 hours of maintenance.
The infamous SS Panzer Division commander Joachim Peiper put his opinion of the King Tiger this way.
Of the great number of panzers which are lost, 3 on 5 of them had to be abandoned and blown up. This is the fate of any mechanical failure and the curse of a continuous withdrawal. The race between armor and anti-tank gun has without a doubt been decided in favor of the latter. Therefore, it appears to me as senseless to go over a weight of 70 tons. More important than heavy armor are high speed and the covering of great distances. In my opinion, the development should center on these requirements.
But his demands were never met. The King Tigers suffered constant breakdowns, drank away all the fuel at a time of fuel scarcity, and their high weight limited mobility over bridges. They were so heavy that only special heavy tank rescue vehicles or other King Tigers could tow them in an emergency. On top of all its shortcomings, the King Tiger was very expensive to produce. The final cost of 321,500 Reichsmarks per unit. In rough estimates, this would amount to $2.8 million today. It cost twice as much as a Panther tank. All these things compounded at a time when Germany was unable to afford it, causing the armoured columns meant to spearhead the war to grind to a halt. We could only guess what this tank could have been if the German engineers had more time and resources. This is the M4A3E8 Sherman. It was the last modification of the US Sherman tank series during World War II, with production starting in August 1944. The tank was also known as the M4A376WHVSS and featured a welded hull armed with a 76mm gun. The W in the name denoted wet ammunition storage that we'll tell you about later in our film. The tank was built with horizontal volute spring suspension, better known as HVSS, giving it improved ability to cross broken ground. And with wide tracks, it had much lower ground pressure and a better ride than previous Shermans. Because of this, the M4A3E8 gained the nickname the Easy 8. The Easy 8 is famous in films for being the tank portrayed in Fury, but for this film, we've painted ours as Besotten Jenny, or Jenny at the Gates, from the Battle for Castle Itter. My name is David Webb, and this is Blue Paw Print. The Easy 8 had a crew of 5. The driver, the bow gunner, the loader, the gunner, and commander. The Easy 8's hull was 20 feet 7 inches long, the overall length increasing to just under 25 feet when the main gun overhang from the hull front was taken into account. It was just under 10 feet wide at its widest point on the hull, and 7 feet 5 inches wide between the midpoint of each track. This gave it a lower center of gravity than earlier variants of Sherman, which in turn meant it was less likely to topple over if it slipped off a road or onto an embankment or similar. Its internal weight distribution allowed the Easy 8 to cross ditches up to 90 inches wide. The Easy 8 was 9 feet 9 inches tall from the bottom of the track to the top of the turret. This was tall for a combat tank, much taller than the equivalent British Cromwell, which was a whole 19 inches shorter than the Sherman. The extra space allowed for wet underfloor ammunition stowage lockers, which significantly improved the chances of crew survival. The Easy 8 Sherman could go over vertical obstacles up to 2 feet high, climb slopes up to 30 degrees, and wade through water 3 feet deep without any preparation. It had a fully loaded combat weight of 74,200 pounds, making it 3,600 pounds heavier than the M4A1 fitted with a 76mm gun. But this extra weight was more than offset by the improved performance of suspension and track, giving it lower ground pressure. The upper frontal armour consisted of a one-piece hull front, as opposed to multi-piece hull fronts on other welded models, such as the M4 and the M4A4. As any weld line is a potential weak spot, their removal aided the overall protection capability of the tank's armour. The front slope angle was 47 degrees from the vertical, instead of 57 degrees on variants like the M4 and M4A1, which looks initially like a backward step, as the steeper the angle, the more effective the armour. But the Easy 8 had frontal armour 2.5 inches thick instead of the 2-inch armour of regular Shermans. So overall effectiveness of the frontal armour was better than the other models. The one-piece welded armour lower hull front carried armour between 2 inches thick, where the transmission housing sloped, and 4.25 inches thick, where the housing sat vertically. The vertical side sponson armor thickness on the EZ-8 was 1.5 inches. The rear armor was 1.5 inches, and the underfloor armor was 1 inch thick, with the top deck armor 3/4 of an inch thick. The armor was an all-steel homogeneous plate, meaning the steel was one solid layer, as opposed to other tank types that used multi-layered, face-hardened steel, which could be prone to cracking and spalling. The EZ-8 had larger driver and bow gunner escape hatches than earlier Sherman variants to allow ease of escape if and when the Sherman was hit. In common with all other Shermans, there was also an escape hatch set into the hull floor. The EZ-8 turret was a brand new design derived from that used on the experimental T-23 medium tank. A new turret type was required because of the extra length, larger breech, and larger counterbalance weight fitted to the M1 76mm gun. The turret was a single-piece steel casting, 2.5 inches thick all round, with a 1 inch thick turret roof. The 2.5 inch thick turret frontal armor was a 1/2 inch thinner than that on earlier Shermans. But the new M62 gun mantlet, specifically designed to help carry the 76mm main gun, was fitted across the entire front of the turret, adding an additional 3.5 inches to the overall thickness of the turret's frontal armor. The turret came fitted with a commander's cupola, with 6 vision blocks inset into it to give a 360-degree view when the crew buttoned up. All T-23 turrets fitted to EZ-8s had 2 hatches, one for the commander and gunner, and one for the loader. Inside the turret basket was largely cut away, the commander and loader's seats attaching directly to the turret ring, so that they rotated with the turret. The EZ-8 turret used a hydraulic system powered by an electric motor. The unit sat in front of the gunner. The turret could be traversed either through a power grip held by the gunner or by an override handle used by the commander. The system had handles to operate the traverse if the hydraulics failed. The traverse speed was excellent. The turret could rotate 360 degrees in just 17 seconds. This gave it a significant advantage over its German opposite numbers. A Panzer IV took 26 seconds to fully rotate its turret, and the Tiger took nearly a minute. The engine was an 18-litre Ford GAA 8-cylinder V-shaped liquid-cooled gasoline engine with 4 cylinders per block, both blocks sitting at an angle of 60 degrees. The engine block and casings were made from aluminum to minimize overall weight. The engine had a nominal power output of 500 horsepower, but after powering ancillaries and going through the transmission, there was only 450 horsepower that was effectively moving the tank. The EZ-8 had a top speed of 26 miles per hour, which compares well to the top speed of the Panzer IV-H at 23 miles per hour and the Panther G at 28.5 miles per hour. The drive shaft was coupled low down on the engine rear, which allowed the shaft to exit horizontally and stay this way under the fighting compartment to the transmission unit at the front of the tank. This meant that the fighting compartment was considerably roomier, which allowed space for underfloor wet stowage for the ammunition. In the left rear sponson was an auxiliary generator used to charge the batteries, of which there were 2, and provided power without having to have the main engine running. The EZ-8 had 4 fuel tanks. This gave the tank a fuel capacity of 168 US gallons and gave the tank a range of 100 miles with an average fuel consumption of 0.6 US gallons per mile. The EZ-8 used a system whereby the gearbox, differential, final drives, and their armoured housing were all combined into a single, easily interchangeable unit called the powertrain, which weighed in at 11,200 pounds. The powertrain converted the power output of the engine and directed it to the drive sprockets, either side at the front of the tank. The unit could be removed in one piece. If one part of the unit failed, the whole piece was removed and another one slotted in. This was a massive time saver when maintaining the Sherman in the field. The transmission design didn't allow for track rotation while the tank was in neutral. So unlike other Allied tanks, such as a Cromwell, it couldn't turn on the spot. This restriction gave the tank a minimum turning circle of 62 feet. The driver could select from 5 forward and 1 reverse gear. There were 2 pedals to the driver's front, the clutch on the left and the accelerator on the right. Braking was done via the 2 steering levers, which sat between the driver's legs, one controlling the power to the left track, the other one controlling the power to the right. If the lever was pulled back, that would apply brakes to the appropriate track. The tank turned in relation to the amount of power placed into the final drive on each side of the vehicle. So if a left-hand lever was pulled as far back as it could go, then no power would be going into that track. If a right-hand lever is at the same time pushed as far forward as it can go, maximum power would be applied to the right track, slewing the tank sharply to the left. The opposite use of the levers would mean a sharp turn to the right. Both levers pulled back meant stop. Both levers pushed forward meant all ahead. To start the Easy 8, the driver needed to turn the battery master switch to the on position. Put the gear shift lever in neutral. Then press the foot throttle pedal and pull the hand throttle out about 1/4 inch. Then they would turn the ignition switch to the both position. If the engine was cold, he would prime it with 1 to 3 quick strokes of the primer. He would then turn the starter switch lever to the left. The engine should start readily. If it didn't continue to run, then they would repeat the priming. To drive the vehicle, it was much the same as a manual car. Clutch, select gear, release clutch, and accelerate. The nickname Easy 8 was also thought to come from the suffix E8 placed at the end of the tank's developmental name, and indicated the tank was fitted with the new horizontal volute spring suspension, or HVSS. The suspension allowed smoother travel over rough ground. With the HVSS system, the volute springs were fitted horizontally between the paired bogie wheels. The compression provided by the tank's weight was then converted into lateral force onto the bogie wheels, which in turn spread tension more uniformly along the track. The Easy 8 was fitted with 3 bogie units on each side. Each bogie unit had 4 road wheels set in pairs on each side. There was also a single track return roller above and just behind the lead pair of wheels on each bogie, and 2 double return rollers on each side set above and either side of the central bogie unit. Most importantly, the suspension allowed the fitting of wider tracks, from 16.5 inches wide up to 23 inches wide. This significantly reduced the ground pressure of the tank, allowing travel over softer ground. The Easy 8 could be fitted with 3 different types of track. Because damage to enemy roads was not too much of a concern, most were fitted with T66 steel tracks during the war. The gun fitted to the Easy 8 was a variant of the M1 76mm gun. But because the 76mm was too heavy, the gun was reduced in length by 15 inches and became the M1A1. The barrel length was 11 feet 8 inches. The Easy 8 carried 71 rounds of 76mm ammunition. If encountering a lightly armed tank or truck, the loader would select the M62 APC round. the commander could select a target up to 500 yards distant and still penetrate 3.7 inches of non-sloping armor. But if encountering something like a Tiger head-on, then the loader could use an M93 HVAP T round, which had a tungsten carbide core. A Tiger or similar armored vehicle could be destroyed head-on from a distance of 400 yards. Inside the tank were two .30 caliber M1919A4 Browning machine guns, one in the turret in front of the loader, coaxial with the main gun, and one in the hull front in a ball mount. Additionally, on the turret was a .50 caliber Browning M2 heavy machine gun on a pedestal mount. This was quite awkward to use when the enemy was in front of the tank, as a crew member would have to get out of the tank entirely and stand on the rear engine deck to fire. All main ammunition stowage in the EZ-8 was wet, hence a W in the tank designation. The tank rounds were stored in double-walled armoured bins. The space between the walls was filled with a mixture of water, ethylene glycol to prevent freezing, and a rust inhibitor. If a bin was hit and penetrated, the liquid flowed into the main bin compartment holding the ammunition, drastically reducing the chances of an ammunition fire. Without wet bins, it was calculated that Shermans burned 60 to 80% of the time when hit. This dropped to 10 to 15% of the time with wet stowage. The tank commander would almost always have his head out of the turret to enable him to locate the enemy, and he would use his 8x magnification binoculars to assist with this. The loader stood on the hull floor to the left of the gun when in combat. His job was to quickly select and load the type of ammunition called for by the commander. The gunner traversed the turret and elevated the gun under the instruction of the tank commander. When the gunner thought he had laid the gun correctly on target, he would shout, "On!" The commander, if satisfied, would shout, "Fire!" and the gunner would fire the gun. The main gun was fired either via trigger fitted on a traverse grip or by the gunner stomping on the fire button located on the turret floor in front of his left foot. The driver, bow gunner, loader, and commander all had rotatable M6 periscopes fitted into their respective hatches for viewing when locked down. The commander's hatch was fitted with a vision cupola, which had inset into it 6 vision blocks to give a permanent 360-degree field of vision. The gunner was equipped with a more powerful M10D periscope sight, but most of the time when aiming, the gunner would use the M71 telescopic sight, which had 5x magnification with a 13-degree field of view. The EZ-8 was produced from 1944 to 1945, and 2,617 were built during this time. The EZ-8 served in the US Army for 10 years, then in many other armies all around the world. After World War II, surviving Shermans were further modified and refurbished, so they became different models. But the last of the reworked Shermans left the Chilean Army service in 2003, 59 years after the first HVSS tanks rolled out of the factory. This is the T-34-85, arguably the most important tank of World War II. It was designed for mass production at a rate that no one could match, reaching nearly 1,200 tanks per month in 1944. The T-34-85 had a gun that was a match against late-war German armor, but at the same time it was easier to make and it was delivered in greater numbers. Roughly 3 T-34-85 tanks were produced for each Panzer IV tank. We've modelled the T-34-85 in intricate detail to examine both the engineering decisions that made it so effective and the compromises that came with those decisions. In this video, we'll focus on the most widely produced variant of the tank, the 1944 model from the Nizhny Tagil factory. My name is David Webb, and this is Blue Paw Print. The T-34 was a medium tank. Its hull measured 20 feet long, extending to 26 feet 7 inches with the main gun at full forward position. The tank was 9 feet 10 inches wide and 8 feet 10 inches tall. Its combat-ready weight was approximately 70,500 pounds. The hull was divided into 4 compartments: the control compartment at the front, the fighting compartment in the middle, the engine compartment, and the transmission compartment at the rear. Its crew consisted of 5 men. The 2 hull crew members were seated in the control compartment. The driver sat on the left on a floor-mounted seat adjustable to 3 heights. The seatback could fold flat, allowing him to crawl back into the fighting compartment if needed. The machine gunner sat to the driver's right on an identical adjustable seat. He operated the hull-mounted DTM machine gun. The remaining 3 crew members were positioned in the turret above the fighting compartment. The gunner sat forward of the commander to the left of the main gun. The commander sat directly behind him at the rear left of the turret. The loader occupied the right side. The T-34 had no turret basket, and the crew did not stand on a rotating floor. The hull below the turret was completely open. The T-34 was armed with an 85mm ZIS S-53 gun and 2 7.62mm machine guns. The 85mm gun was the defining feature of the tank. Almost every other design decision revolved around it. It had a barrel length of 15 feet and 3 inches, and a caliber of 85mm. Most guns of this type had the recoil brake and recuperator mounted above the barrel. In the T-34-85, they were moved underneath instead. This lowered the gun's overall profile and reduced the distance between the breech and the rear turret wall. The breech used a vertical sliding block with a semi-automatic mechanism. This meant it opened and ejected the spent casings after each shot. The T-34 carried between 55 and 60 rounds. Most of the load consisted of high-explosive fragmentation shells. A typical loadout included 36 of these, alongside 14 armor-piercing rounds and just 5 sub-caliber rounds. The shells were adapted from the 85mm anti-aircraft gun, which simplified Soviet supply lines during the later stages of the war. The primary armor-piercing projectile was a pointed nose round, which lacked a ballistic cap. This made it easier to manufacture, but increased the risk of ricochet when striking sloped armor and impaired its aerodynamics at long ranges. It weighed 20.6 pounds and left the barrel at 2,625 feet per second. It could reliably penetrate 4 inches of armor at 1,094 yards. Like most Soviet armor-piercing rounds, it also contained a small explosive charge. The sub-caliber shell was built around a tungsten carbide core. It was lighter than the standard shell at 11 pounds and left the barrel at speeds of up to 4,000 feet per second. The sub-caliber shell had several components. An aluminium alloy ballistic cap at the tip reduced air resistance. Behind it, a lightweight steel body shaped like a spool had a 1.4-pound tungsten carbide core in place. A tracer was screwed into the base. The design stripped away as much weight as possible from everything except the core itself. This allowed the powder charge to accelerate the shell to nearly twice the muzzle velocity of a standard round. On impact, the steel body was crushed against the armor plate. The tungsten core carried the concentrated kinetic energy forward and punched through the armor. At 547 yards, it could penetrate between 5.4 and 5.5 inches of armor, enough to punch through the side plate of a King Tiger. Its effective range was limited to around 1,100 yards, and tungsten was scarce, so commanders kept these rounds in reserve for the most dangerous targets. Because the loader was not connected to the tank's internal intercom, communication was often physical. Tank commander Semyon Arya recalled, "I would stick my fist under the loader's nose and he would know that he had to load an armor-piercing shell, and if I held out my palm, he would know to load a fragmentation shell. The gun was fired electrically using a lever on the gunner's elevation handwheel. If that failed, a pull handle on the left side of the breech could be used as a mechanical backup. The gunner grabbed it and pulled down with his right hand. Firing the gun carried real risks for the loader. The breech recoiled between 11 and 12.6 inches, and a direct blow in that confined space could easily break an arm or even kill. To prevent this, the gun featured a safety button on its right side. The loader had to move clear and press the button before the gunner could fire. A long guard with shields was also fitted to the breech to help keep the crew out of the path of the recoil. The 85mm rounds required a much larger propellant charge, nearly 3 times the size of the charge used in the previous tank variation. That meant far more fumes inside the turret. 2 ventilation fans were positioned at the rear of the roof, but they struggled to clear the gases during sustained firing. The loader was the most exposed and could even lose consciousness during prolonged engagements. The fire rate was said to be 6 to 10 rounds per minute, though in practice, the actual combat rate was around 3 to 4. The gunner aimed using the TSH-16, a telescopic sight designed specifically for the 85mm gun. It had a fixed magnification of 4 times and a field view of 16 degrees with a maximum aiming range of up to 2.36 miles. The TSH-16 had 2 main parts. The front of the sight was fixed to the gun cradle and moved with the barrel. The eyepiece was attached separately to the turret roof and stayed in place. This meant the gunner's eye position stayed the same no matter how the gun moved. The sight featured several vertical range scales on a glass plate, each corresponding to a different shell type. The gunner could set the range by rotating a handwheel. This moved the glass plate vertically until the correct range mark aligned with a fixed reference line. The reticle included a central chevron for stationary targets and additional lateral marks for moving ones. This gave the gunner a basic way to estimate range without a dedicated rangefinder. The T-34 was equipped with 2 7.62mm Degtyaryov modernized tank machine guns, or DTMs. The DTM was a tank-adapted version of the standard Degtyaryov infantry machine gun, fed from a drum magazine holding 63 rounds. The tank carried 30 of these magazines in total, giving a combined ammunition load of between 1,890 and 1,953 rounds. The first DTM was mounted in the turret, immediately to the right of the main gun. It was fixed to the gun cradle, so it pointed wherever the barrel pointed. The gunner fired the machine gun electrically using the same trigger lever on his elevation handwheel that he used for the 85mm. 2 toggle switches on top of the elevation mechanism let him select which weapon the circuit was connected to. The second DTM was mounted in a ball mount on the right side of the front hull plate, operated by the machine gunner seated to the right of the driver. Its field of fire was limited, approximately 12 degrees to the left and right, 16 degrees of elevation, and 6 degrees of depression. The machine gunner aimed through a PPU-8T telescopic sight with 2 times magnification. His view of the battlefield was severely restricted. A target was difficult to locate at all unless it was almost directly in front of the tank. If the tank encountered a position it could not overcome, the commander could trigger 2 tank-adapted naval MDSH smoke canisters mounted on the rear hull. They produced a dense white cloud within seconds. The cloud lasted up to 10 minutes, enough to mask withdrawal or cover the tanks following behind. The T-34 was designed to operate alongside infantry and exploit breakthroughs at speed. Its armor reflected that role. The hull was designed in such a way that it allowed it to be built fast and in enormous numbers. Soviet factories used automated submerged arc welding to join the plates, a far faster method than manual welding and requiring less skill, while also producing strong, more consistent seams. This mattered greatly because much of the workforce assembling these tanks consisted of teenagers and workers with little or no prior experience in heavy industry. The upper and lower front plates were both 1.77 inches thick, set at 30 degrees from horizontal. That angle increased their effective thickness to 3 inches. The upper plate housed the driver's hatch, the machine gun embrasure, and 2 towing hooks. The driver's hatch had 2 prismatic viewing devices, protected on the outside by hinged armored covers, which crews referred to as eyelashes. Each side of the hull was made from 2 plates welded together. The upper plate covering the sponsons was angled at 50 degrees from horizontal. The lower plate was vertical. Both were 1.77 inches thick, though the angle of the upper plate increased its effective thickness to approximately 2.32 inches. The rear of the hull consisted of an upper and lower sloped plate, along with 2 gearbox housings. The upper rear plate was hinged and bolted in place, so it could be removed for engine access. A large round hatch in the center of the rear upper plate provided access to the transmission compartment. The hull roof was 0.79 inches thick. The floor consisted of 2 plates joined by a welded seam. The front plate was 0.79 inches thick and the rear plate was thinner at 0.51 inches. A narrow escape hatch for the driver and machine gunner was located at the front of the floor. The T-34-85's turret was the main difference between this tank and its predecessor. Its turret expanded the internal volume by approximately 1.5 times more than the T-34-76, enough to fit a dedicated gunner inside for the first time. The ring diameter was increased to 63 inches to accommodate the larger gun. To prevent the turret from catching on the hull when rotating, it was mounted on a raised collar, a distinctive raised neck visible from the outside of the tank. This added 8.7 inches to the overall height of the tank, and unlike the older T-34-76, this tank was now an easier target to spot and to hit. The main body of the turret was cast as a single piece with only the roof welded on separately. Cast armor offered slightly lower ballistic resistance at the same thickness as the German armor, typically constructed from rolled plate. But it allowed complex curved shapes to be produced more quickly and with less skilled labor. The frontal shield was cast together with the turret body, removing the need for a weld at the most vulnerable point. The turret was rotated by an electric drive, turning at 24 to 26 degrees per second. A full rotation took between 14 and 15 seconds. Unlike the hydraulic systems used in many German tanks, the electric drive was independent from engine speed. The turret traverse mechanism was controlled by a single lever that switched between electric and manual operation. In the vertical position, it engaged the electric motor for rapid turret rotation. When moved to the horizontal position, it enabled precise manual aiming. On the outside, 2 ventilation fans were fitted at the rear of the turret roof, covered by armored housings that crews referred to as mushrooms. The commander's cupola was positioned on the rear left side of the turret roof, directly above this station. The main gun ammunition was distributed across 4 locations. 4 shells were stored on the right wall of the turret in a quick-access clamp rack. Another 12 to 16 were kept on a shelf in the turret bustle directly behind the loader. These were the most accessible rounds in the turret. The remaining 39 to 40 rounds were stored in the hull. 35 were in 6 metal boxes bolted to the floor. The last 4 or 5 were secured upright, 2 directly behind the bow machine gunner, and the rest in the rear corners of the fighting compartment near the engine firewall. Retrieving rounds from the floor boxes was the most demanding part of the loader's work. As the turret rotated, he had to move with it or be knocked off his feet by the moving breech. He stepped on the ammunition boxes fixed to the hull floor, retrieved the next round, and cleared the breech path before each shot. Due to the cramped space, loaders were usually under 5'7" tall. 15 machine gun magazines were placed directly in front of the machine gunner for immediate use. 4 more were mounted on the right wall of the turret for the loader. The remaining magazines were stowed throughout the hull. The T-34 was powered by the V-234, a 12-cylinder V-type diesel engine producing 500 horsepower at 1,800 RPM. It was the first mass-produced tank diesel engine in the world. The engine had originally been developed by a factory that built aircraft engines, and that heritage showed in its construction. The block and crankcase were cast from an aluminium-silicon alloy, keeping the dry weight down to around 1,650 pounds. The total displacement was nearly 39 litres. Because the engine ran at low RPM, it needed large cylinders to generate enough torque to move the tank. The bore measured 5.9 inches and the stroke 7.4 inches. The low RPM and high compression ratio made the engine fuel efficient, giving the tank a road range of around 186 miles. That was critical to its role as a breakthrough tank. The engine featured a dual starting system. The primary method used a 15 horsepower electric starter. If batteries failed or temperatures dropped too low, the driver could start the engine using compressed air fed from 2 cylinders at his feet. The tank had a top speed of 34.2 miles an hour on a clear road, just a few miles an hour short of a fully loaded classic London double-decker bus. Although operational speed was typically lower across rough terrain. On the battlefield, speed and maneuverability became the T-34's primary defense as it lost its armor advantage. Tank driver Nikolai Zheleznov recalled, "The tank charges at high speed, zigzagging and constantly changing direction. If it heads straight ahead, you might as well say it's headed for the afterlife." The T-34 carried its fuel in 8 internal tanks with a combined capacity of 144 gallons. These were divided into 3 specific groups. The left and right side groups each consisted of 3 fuel tanks, 2 in the fighting compartment and 1 in the engine compartment, holding 52.8 gallons per side. The remaining 2 fuel tanks made up the stern group, located in the rear transmission compartment, which held a combined 38.3 gallons. The internal side fuel tanks presented a serious risk. 2 of them sat inside the fighting compartment alongside the crew. A penetrating hit through the side armor could pierce them directly. But because the T-34 ran on diesel rather than gasoline, the liquid fuel itself was difficult to ignite. A hit to the full fuel tank would shower the crew in diesel, but it rarely caught fire. An empty fuel tank, however, was a different matter. The vapor that accumulated inside it could detonate with the force of a high explosive shell. Most crews went into battle with full fuel tanks, accepting the extra weight. A full fuel tank left less space for vapor to build. 3 additional cylindrical drums were carried on the outside of the hull, each holding 23.8 gallons. These external tanks were not connected directly to the engine. They were used to refill the internal tanks during stops. The T-34 had a road range of approximately 186 miles on internal fuel tanks alone. Fuel consumption varied between 0.5 and 0.7 gallons per kilometre, depending on the terrain and load. The cooling system consisted of 2 separate circuits, one for the water and one for the oil. The water circuit held 19.8 gallons. It was sealed, and internal pressure raised the boiling point of the coolant to around 230 degrees Fahrenheit. The driver monitored coolant temperature through a remote thermometer, with normal operating temperature reaching up to 221 degrees Fahrenheit. A large centrifugal fan was mounted directly on the engine flywheel, bolted to the crankshaft. It ran whenever the engine was running and drew in air through armoured shutters on the engine deck, pulled it across the radiators, and expelled it through the shutters at the rear of the hull. The oil circuit ran alongside the water system. A tubular oil radiator was mounted onto the left water radiator. Oil thickened in cold weather, and the pressure it generated was enough to burst the core. During winter, the oil radiator was replaced with a straight pipe. The driver controlled the tank using 2 vertical steering levers, one on each side of his seat, along with 3 foot pedals and a gear lever to his right. The steering levers operated the side clutches and brakes for each track. Pulling a lever halfway disengaged the clutch on that side and produced a wide turn. Pulling it fully applied the brake, tightening the turn. Early versions required significant physical effort, up to 132 pounds of force per lever. Later models introduced a spring-assisted servo mechanism that reduced this to around 44 to 55 pounds. The 3 pedals followed a similar layout to a manual car. The left pedal operated the clutch, disconnecting the engine from the transmission for gear changes. The center pedal controlled the transmission brakes, and the right pedal was the accelerator connected directly to the fuel pump. The gear lever operated a 5-speed gearbox. The transmission was mounted at the rear of the hull. The lever connected the gearbox through a long mechanical linkage that ran under the floor. Changing gears required considerable force if the linkage was not kept in precise adjustment. The machine gunner seated next to the driver was sometimes called on to help with a particularly difficult gear shift. A hand throttle allowed the driver to hold a steady engine speed without keeping his foot on the accelerator. The V234 could be started in 2 ways. The primary method used an ST700 electric starter producing 15 horsepower. Before engaging it, the driver turned on the battery master switch, confirmed the gear lever was in neutral, and selected which group of fuel tanks would feed the engine. The fuel and lubrication systems then had to be primed manually. The driver pressurized the fuel tanks using a hand air pump near his feet. He waited until pure fuel appeared before closing the drain valve. He then ran a mechanical oil pump to circulate oil through the engine block before ignition. Skipping any of those steps risked a dry start, which caused rapid wear to the internal components. Once the systems were primed, the driver depressed the foot throttle slightly and pressed the starter button. The starter could not be held for more than 4 to 5 seconds at a time. The driver had to wait 10 to 15 seconds between attempts to avoid overheating the motor or draining the batteries. The crew switched to compressed air backup if the batteries were dead or if the temperature was too low for the electric starter. The driver opened the valves on the 2 cylinders in front of his feet, depressed the clutch and fuel pedals, and then turned a reductor valve to send high-pressure air directly into the cylinders in the correct firing sequence. The air forced the pistons down and rotated the crankshaft until the engine caught. Once the engine fired, the valves had to be closed immediately. The engine had to warm up before the tank could move. The driver closed the radiator shutters and ran the engine at 700 to 800 RPM until the oil reached 50 degrees Fahrenheit, then increased to 1,200 to 1,600 RPM until it reached 86 degrees Fahrenheit. The tank was not ready for movement in higher gears until both oil and coolant temperatures reached at least 113 degrees Fahrenheit. The T-34 used a 5-speed gearbox. This was an upgrade over the 4-speed unit fitted to earlier models, which had been one of the most criticized components of the original design. The new gearbox used constant mesh gears with sliding tooth clutches, which made shifting easier and reduced mechanical stress on the drivetrain. The rear-mounted layout kept the drivetrain compact. Power started at the engine and passed through a dry, multi-plate clutch on the flywheel. From there, it moved through the gearbox, then onto a pair of side clutches and strap brakes that controlled steering. Finally, it reached the rear drive sprockets through single-stage reduction final drives. The transmission remained a known weak point despite the improvements. The gearbox was prone to wear under hard use. Soviet engineers addressed this with a practical solution. A hinged rear plate and removable engine roof allowed mobile maintenance units to swap out entire engines and gearboxes without sending the vehicle to the rear. A tank that could be returned to the fight quickly was worth more than a technically superior vehicle that could not. The T-34 used a Christie-type suspension system, inherited from the earlier BT Soviet tank series. Each side had 5 road wheels. Each of the 5 road wheels operated independently, connected to large cylindrical coil springs housed inside armoured shafts within the hull. The springs were protected, but they ran through the interior of the fighting and engine compartments, taking up precious space inside. The front springs were mounted vertically, with one spring nested inside another, to absorb the impact of obstacles. Each track was 19.7 inches wide and made up of 72 links. The wide tracks kept ground pressure low and allowed the tank to cross terrain that heavier vehicles could not. The suspension had no hydraulic shock absorbers. This produced severe vibrations at high speed. Accurate fire on the move was extremely difficult, and crews experienced considerable fatigue during long journeys. Due to a severe shortage of rubber, the mid-war all-steel wheels on Soviet tanks generated a lot of noise. By 1944, increased synthetic rubber production allowed the T-34-85 to have rubber-tired wheels, which reduced both noise and crew fatigue. In a typical engagement during the summer of 1944, a platoon of 3 T-34-85s would be used to seize a road junction, ahead of a retreating German column. Each tank would carry 7 or 8 infantrymen riding on the hull. On rough dirt roads, a platoon of T-34s could move fast enough to beat the enemy to the position. Once in position, the commander would order the infantry to dismount and take cover. The commander's tank and a second tank would take concealed positions, ideally behind a low rise, while a third tank worked its way around the far side of the battlefield. When a German column entered the engagement area, the Soviet platoon would normally try to engage the armoured vehicles first. If the column was led by a Panzer IV and covered at the rear by a Stug 3, one T-34 would fire on the rear vehicle to limit the column's ability to withdraw or manoeuvre, while the commander's tank engaged the lead vehicle. At a range of around 500 meters, the 85mm gun of the T-34-85 was capable of penetrating the frontal armor of a late model Panzer IV. Knocking out the lead tank was crucial, as it could block the road for the rest of the column. After that, the Soviet fire would shift to the transport vehicles and infantry. High explosive shells from T-34-85s, combined with small arms fire from the dismounted infantry, would be used to suppress the German troops before they could deploy anti-tank weapons effectively. If the Stug 3 at the rear managed to use an embankment or cover in the ground to avoid direct fire, a third T-34 would usually engage it from the flank. Once the German armoured vehicles had been disabled, the rest of the column could be forced to stop or disperse. The T-34 was not the most powerful tank of the war. In a straight fight at long range, a Panther or a Tiger held a distinct advantage. But it was capable of operating where heavier vehicles could not. It was fast enough to maintain the pace of an offensive, and most importantly, it was easy and fast in production. If you'd like to find out about a more obscure Nazi superweapon, then check out our video on the V3 London gun.